Do you know how to use Hashin criteria to model progressive damage in 3D continuum composite materials? Let's find out in this video.
In this training package, we will explain the VUMAT subroutine for progressive damage of 3D continuum composite element using the Hashin failure criterion. The following questions are answered by the materials in this bundle. When can we use these subroutines? Which theories are applied to composite materials' three-dimensional elasticity? Which hypotheses are used to the continuum element's progressive Hashin failure? Following that, subroutine writing explanations and related workshops will be discussed. To get the most out of this training package, you should first go through the introduction to UMAT and VUMAT subroutine and Abaqus training program, which is available on the website. After you've finished with this package, you can move on to the advanced package to learn more about UMAT and VUMAT subroutine writing. This package includes almost 90 minutes of the introductional video, which includes simulation-related items, tips, and information, as well as practical examples for writing these subroutines. And all simulation files, subroutines, along with other items are provided to you. First and foremost, you must understand when this subroutine is required. VUMAT is the subroutine in question, so it uses the explicit solver, and in addition to being used in dynamic problems, it is also used in static and quasi-static problems with considerations amplitude and time, resulting in comprehensive use of this subroutine in solving problems. Note that whether or not we can use this function relies on whether or not using the shell element in Abaqus is the best solution for your case. As you may know, Hashin failure criterion for shell element is available in Abaqus for both damage and progressive damage of composite materials, but sometimes you cannot use shell element. For example, the thickness of one dimension is not less than other dimensions. So, using shell and continuum shell elements are incorrect. Therefore, you cannot use Hashin failure criterion to detect damage initiation and implement progressive damage for composite material model in Abaqus. For instance, consider a tube with a large thickness as seen in the figure. The elasticity of composites with the 3D continuum element will be discussed in the next stage. You can see the strain-stress relationship in composite materials, which C' is stiffness matrix. The stiffness matrix in a three-dimensional continuum is calculated based on elasticity properties in each direction. Note that several mechanical properties are calculated in this shown scenario dependent on other mechanical properties. For example, the Poisson's ratio is calculated as follows. In addition, there are a few items that are required for the material's stability that must be addressed in the information booklet, which is available in its entirety here. The next stage is to propose a hypothesis regarding how Hashin damage initiates. The fiber failure and matrix failure formulas are presented in both tensile and compressive states. If any of these conditions are met, 3D Hashin damage initiation occurs. Another criterion which has been added to complete the damage initiation mode is shear failure, which will occur as the shear stress to shear strength ratio increases. What will be the reduction of properties according to the 3D Hashin criterion after the damage initiation? The stress can either stay constant with no change in characteristics, or it can diminish slowly, exponentially, or abruptly. We'll be doing a gradual reduction in this package, and it'll be of the exponential type, which is a more complex type. Once you understand this, you'll be able to utilize the linear type as well. For instantaneous properties reduction, you can use the USDFLD subroutine, which is covered in other packages to make your subroutine writing method easier. Once the damage has been detected, the formulas in this section can be used to calculate each of the damage parameters. There are parameters in these relationships, such as the Hashin failure criterion, in each mode, which will be determined based on the previous slide relationships, such as FD, which is the fiber failure criterion index. To calculate damage parameters, other parameters are also required, like toughness, strength, element characteristics, and elastic matrix component. As I mentioned before, LC is the characteristics element, which is the problem input booklet. The same will be true in other circumstances. The coefficient C, which is present in all relations, is the stiffness matrix coefficient. The other two factors, damage fiber and damage matrix, will be calculated in the same way by the parameters from the previous sections.
Let's go and see some parts of the VUMAT subroutine.
According to the flowchart on the right side of the figure, after the subroutine has started, you must enter the props at the problem input, which can be seen from line 53 to 87. Elastic characteristics, tensile, shear, and compressive strength, shear stiffness, reduction coefficient, intralaminar toughness, which includes toughness for fibers and matrices in both tensile and compression states, and shear toughness for different plates are all defined in these lines. Then state variables are introduced, which are described as comments in this document. It should be mentioned state variables 1 to 9 for damage variables, state variables 10 to 15 for strains, and state V16 for element removal status. State V17 up to 23 are three-dimensional Hashin damage initiation criterion, and state V24 up to 29 elastic are stress matrix components. Note that in line 115 we specify that our element is active by placing the number 1 in the desired parameter. However, if the value is 0, our element becomes inactive. The flowchart specifies the other intermediate parameters: Poisson's ratio in various planes, as well as failure strains in various tension and compression states for fibers, matrix, and shear are included here, and we will need them in next calculations. The stiffness matrix is defined with 0 values between lines number 130 and 135. Then the stiffness matrix must be defined in the next lines where our model enters the undamaged area and the formula for all of its components must be defined here according to the presentation.
Okay, that's it for now. You can have access to the full tutorial of the subroutine along with the subroutine file via the link in the description below. But for now, let's see this subroutine in action in Workshop 1.
Here in Workshop 1, VUMAT subroutine has been implemented using continuum element for composite materials. A rigid bullet has impacted on an 8-layer composite plate with a layer thickness of 0.2 and page dimensions is 100 to 100 in this workshop. The initial velocity of bullet is 300 with a friction coefficient of 0.25. The mechanical properties of the composite plate are provided here, including density and strength, as well as all of the coefficients required to run the subroutine. Note that the adhesive is employed between the layers, and adhesive behavior is linear in elastic phase and also in linear in softening phase. And the properties will be reduced as seen in this graph. The maximum traction criterion for damage initiation and reduction of material stiffness in the form of softening based on Benzegar-Kenin criterion will be used. You can see the formulation here. This section contains all parameters including adhesive stiffness in normal and shear directions, normal and shear strength, and fracture energy for normal and shear modes with the Benzegar-Kenin coefficient. In the next section, we will discuss how to simulate using this subroutine. Spheres, bullets, and plates should be modeled according to the dimensions in the presentation. We create 8 pages of the same size. Mention that you could create a plate and stack it in the assembly section as a second method of use. Bear in mind that you'll have to attach the appropriate subroutine in the job module. You can see the movement of the bullet and the rupture in the results section after the problem is solved. We can analyze the output for each of the state variables if we wish to study each result in relation to the data in the subroutine. There is some information in general, such as S, as well as damage variable ranging from 1 to 9. SDV1, SDV2, SDV3, SDV4, and so on until SDV9. From option 17 to 23, Hashin standard numbers can be displayed. And other items such as elastic strains and stresses are shown here as well. By selecting this option, the direction of the fibers can also be visible in blue. The cohesive damage index can be examined by looking at the damage initiation criteria.
Okay, now, let's see another example and its results for better understanding.
In this workshop, we will implement the VUMAT subroutine for a static model. In this workshop, we demonstrate that this subroutine may be utilized in statistic mode, even if the issue differs from the dynamic explicit solver type. This is a simple tensile loading on a hold plate whose dimensions are specified in this image. Also, for simplification in modeling, a quarter of the model has been simulated. The fibers have a 0-degree angle, and the thickness, sheet dimensions, and hole radius are all defined. This section specifies the amount of displacement as well as the mechanical properties of the composite materials, such as elasticity, density, strength, and shear strength reduction coefficient. The desired subroutine will be implemented in the next section. This option is selected if we want the results in the form of animation when analyzing. Because the shear loads are higher around the hole, they will cause rupture. Set the scale factor to 1 to see the distortion more clearly. Here you can see the maximum amount of shear stress caused failure. The damage index is clearly obvious here. Also, from state V17 to 23, the Hashin damage initiation criterion can be noticed. We'll look at the energy to check if the issue is entirely quasi-static. Here, kinematic energy and internal energy diagrams are called. We must adjust the default values of the axis to the numbers indicated in the axis options section if we want to observe the dynamic failure region with sufficient precision. The chart is as follows by default. This is one of the capabilities of VUMAT subroutine that we can solve quasi-static problems as well as dynamic problems. Check that the values required for subroutine inputs are correct and that they have been tested. Remember to pay attention to the time and mass scale when solving quasi-static tasks, as well as the ratio of kinetic energy to internal energy, which should be between 1 and 5%. To fix this problem, we can alter the meshes and increase the time. If we increase the time value, we see that the ratio of kinetic energy to internal energy improves. As previously stated, the amplitude should be entered smooth to avoid the loading rate becoming dynamic.
Hello everybody and welcome to our new video training package of Abaqus. Introduction to 3D Continuum Abaqus Hashin Progressive Damage for Composite Materials using VUMAT Subroutine. This package includes these sections. Workshop 1. Simulation of 3D Hashin Damage Initiation and Gradual Progressive Damage using VUMAT Subroutine in Impact Analysis. Workshop 2. Simulation of damage initiation and gradual progressive damage in tensile test of plate with hole using VUMAT subroutine. Thank you for taking the time to watch this video. We hope it will be useful for you.